Okay, so today we're going to begin talking about hypothesis testing, which actually is something we're going to do in all of the remaining sections. So we've got 6 remaining sections left, 3 in chapter 8 and 3 in chapter 9, and all of them are going to have some hypothesis testing in them. So 8.1 is kind of the introduction. So this guy has a lot of information. So if you need to come back to this video at some time, you can do that. But we're going to get into more specifics of hypothesis testing in 8.2 and 8.3. So here we have to get rid of all of the definitions so we know kind of the setup and the procedures so that we can use them in more specific situations in 8.2 and 8.3. So a hypothesis, when we're talking statistics wise, I think you know what a hypothesis is like in science, but for us, a hypothesis is going to be a claim about a property of the population. So it could be a claim about the proportion. It could be a claim about the mean. It could be a claim about the standard deviation. But that would be our hypothesis. A hypothesis test is a test of significance, which is basically going to test the hypothesis, the claim that we have. When we do hypothesis testing, every single type is going to use null hypothesis and alternative hypothesis. The null hypothesis is a statement that the value of the parameter, so again, could be any of the parameters that we've studied, is equal to a claimed value. So not less than, not greater than, equal to a claimed value. Null hypothesis has its own symbol. It's a capital H with a subscript of 0. And that's what we'll use. We won't write out null hypothesis. They'll ask you to find H sub 0, which means the null. Then we also have the alternative hypothesis, which we abbreviate symbol-wise as H with a subscript of 1. So H1 is the alternative hypothesis, and that's a statement that a parameter has a value different from the null hypothesis. Now, when we say different, that could be various inequality symbols. Some of the cases that we're going to look at could be less than, could be greater than, could be not equal to, but somehow different from the null hypothesis, which is always an equal. So null is always an equal. The alternative is any of our other symbols. Significance level is our alpha, and that is a probability value that's used as the cutoff for determining when a sample has significant evidence against the null hypothesis. So what this basically means, if I'm trying to use less mathy terms, is the significance level is representing our probability of rejecting the null hypothesis mistakenly. Meaning that if our null hypothesis is that the mean of the population equals 60, our significance level, our alpha, is the probability of us saying, no, the mean of the population couldn't be 60, and that being a mistake. So that's what our alpha represents, is it's the probability of us saying, no, that's not right, but us doing that incorrectly. When we do hypothesis testing, we're going to use 2 different methods. We're going to use the p-value method, and we're going to use the critical value method. So for those, we need to know what a test statistic is. And a test statistic by definition, is a value that's used in making a decision about the null hypothesis. We find the test statistic by converting our given sample statistic to a score. Now, this could be a z-score or it could be a t-score, because remember in chapter 7 we introduced the student t-distribution where we had t sub alpha over 2. So sometimes we'll be using z for our test statistic and sometimes we'll be using t. P-value, we briefly introduced p-value at the beginning of this course, and what the p-value is the probability of getting a value of the test statistic that is greater than or equal to the sample test statistic, and this is assuming that our null hypothesis is true. When we are trying to find a p-value, we will use the function of normal CDF in our calculator. So write that there just so you remember that when we're finding p-value, that's what we're going to use. And then for the critical region, this is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. So rejecting the null hypothesis means we are saying, no, that value can't be true for that parameter. And when we do hypothesis testing, you would think that the opposite of rejecting is to accept, but we never actually say accept. Everything with hypothesis testing is either reject or fail to reject, which just basically means that we either have enough evidence to say that the claim is definitely wrong, or we say we don't have enough evidence to say that the claim is wrong, which means that it's possible that the claim is correct. But we never actually say, yes, the claim is correct. We just say there's not enough evidence to say that it's wrong. So we're always doing reject or fail to reject. Critical regions, depending on which type we're using, we're either going to use inverse norm or inverse t. Obviously, if our test statistic is t, we'll use inverse t. If it's z, we'll use inverse norm. The critical region is also sometimes called the rejection region. And we will draw pictures of the rejection region as we go. So what I have here are the various steps of our hypothesis testing. You will need for the first couple times, maybe for this entire homework, probably need to look at these steps. But once we get to the next section and we're doing the same steps again, at that point you should hopefully know them. And we're, like I said, going to continue using hypothesis testing in all of the remaining sections. So these should help you. And so you'll need to study these because you do not get to use this on, the quiz or the test. Well, I guess quiz or final exam, because I don't think that anything like this is going to fit in your box. So you do need to know these, so start studying them. But we are going to follow these, and every example that I'm going to do, I'm going to walk through this. So first we have to identify the claim that's to be tested and express it in symbolic form. So that means, okay, what's my parameter? Is it P? Is it mu? Is it sigma? Whatever the case may be, am I saying that P is equal to a specific number? Am I saying that mu is less than a specific number? That's what it's asking us to do in step 1. Step 2 is to give the symbolic form that must be true when the original claim is false. So that means that we're going to work toward identifying, which is step 3, what is our alternative hypothesis and what is our null hypothesis. So if our claim is that mu is equal to a number, then if that's false, then that means that mu is not equal to that number. So we're kind of identifying what the opposite would be. And remember that the null hypothesis always has to have an equals, and we're deciding whether our alternative hypothesis should have a greater than, a less than, or a not equals. So the alternative hypothesis does not contain equality. There are no equal signs, only a not equals, a less than, or a greater than. Null hypothesis has the equals. Then we select our significance level alpha based on, it says, the seriousness of a type 1 error. What that basically means is how sure do we want to be? The smaller we make our alpha, the more sure we are of the result. So when they do studies for like medications and things, usually they're going to be more stringent. So they're going to have, like a 0.01. 0.05 and 0.01 are the most common. Sometimes you see a 0.1, but that hypothesis testing is a little more lax. So since it's not as stringent, it's not going to be as accurate. You also have to consider, like, what is the seriousness of what you're studying? If you're wrong, are people going to die? Then that's pretty serious, and we should probably choose something smaller. If it's not something that's that serious, then we might use a hypothesis testing significance level that's bigger. Once we've selected our significance level, then we're going to be able to identify the test statistic. So we're going to find our t or z score. This says normal is z, so that's z-score. This says normal, t, and chi-square. We won't do a ton with chi-square. We have that over here. So we'll look at it briefly in this section, but we will not use chi-squared in the remaining section. So we introduce it. It's just a specific distribution like normal distribution is, but we won't use it a ton. Here's where we split off, and you can see that in the chart. There are two different ways to test our hypothesis, the p-value method and the critical value method. You do need to know both of them. So it's very, very important that if the directions tell you to use a specific method, that you use that method. If they don't, then my suggestion is to rotate them. I believe that unless the directions say otherwise, I usually give the information that would, regardless of which method you chose, that you'll be able to tell if your answer is correct or not. But p-value method will find the value of the test statistic and the p-value, and then it's very specific. We just look at what the p-value is. If the p-value is less than or equal to the significance level, we reject the null hypothesis. If the p-value is bigger than the significance level, then we say we fail to reject it. For the critical value method, we find the test statistic and the critical values, meaning we're looking to find whether those values are in the rejection region or not. And if the test statistic is in the rejection or critical region, then we reject the null. We fail to reject it if our test statistic is not in the critical region. Step 8, you'll get really tired of step 8 because you have to write out sentences on step 8. We have to restate our decision in non-technical terms, which still addresses the original claim. So on the back of the notes, I go through how you should word your conclusion. But you basically, go through you use the same wording every single time. Here is some information about which test statistic you should be using. So a lot of it is based on what our parameter is. So if we're looking at a proportion, we're always going to be using the normal distribution and using Z as our test statistic. If we are studying a mean as our parameter, then it depends on what we're given as to whether that's going to be a T distribution or a Z distribution. And you can see here, if we don't know our standard deviation and our population is normally distributed, or if we don't know it and n is bigger than 30, then we can use our T. If we don't know the standard deviation and is not known and greater than 30, then we can use the Z distribution. Standard deviation and variance both use a chi-square. It's a stricter requirement, which is why we don't focus on the chi-squared a lot, but this is the formula to find the test statistic. So some of your homework will just ask you, find the appropriate test statistic. So you look, you say, okay, is it a proportion? I'm going to use this formula. Is it a mean? I'm going to use this formula. Is it a standard deviation? I'm going to use this formula. So those are the different values that you're going to need. You do not have to memorize these formulas. Again, you'll have to know when to use each one, but on the quiz, these will be given to you. So you do not have to memorize them. The other thing that you have to know when it comes to hypothesis testing is what type of tail we use. So when we are doing these hypothesis tests, it's going to ask you in your calculator whether to use right-tailed, left-tailed, or two-tailed test. This is always based on the sign of the alternative hypothesis. So notice this isn't the null, this is the alternative hypothesis. If we use a not equal to, that's a two-tailed test. If we use a less than, it's a left-tailed test, which I remember L and L. If it's a greater than, then it's a right-tailed test. When we are using these tails, what ends up happening is this gives us our rejection region for the critical value method. So if I make like a little key here, this represents where the rejection region for the critical value method would be. So critical value method. So on a two-tailed test, the rejection region is going to be over here and over here. So if our test statistic falls anywhere in this shaded color, then we would reject our null hypothesis. For left-tailed, the rejection region is just over here. And for right-tailed, it's over here. All right, so then if you flip it over, we've got even more information. There's so much when we introduce hypothesis testing. And right now you're probably feeling like, oh my gosh, this is so overwhelming. I promise you, when we get into this, once you've done this over and over and over again, it's going to become super easy. People usually don't struggle very much with this once they get going. So in 8.1, you might struggle a little. But it's super important. Please don't cheat yourself on doing your practice problems, because if you don't practice, this is going to be something that will continue to be a struggle. So please, 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 if you do your practice, I don't think that you'll eventually think that this is difficult. So this kind of tells you whether we are going to use a left-tailed or right-tailed test, and kind of gives you the different values for where p-value would be and where the test statistic would be. So we'll refer back to this as we go through the examples. This very last thing is how we word our conclusion. So how we word the conclusion is based upon whether the original claim does or does not include equality. So notice these first two, it says does not, and the second one includes. So that's the first thing, is that you look at the original claim. Does it have an equal sign, or does it have one of the other symbols? Once you determine that, then the other part is based upon whether you reject or fail to reject. So we've got 4 different possibilities. Either it does or does not have equality, and either it rejects or fails to reject, and the way that we word it is slightly different. You have to use these exact words. This is not something where we kind of paraphrase. Every single time we use the exact same words. Okay, so let's actually take a look at our examples, so how you're actually going to be using all of this information. So example 1, it says claim 20% of adults smoke. A recent Gallup survey of 1,016 randomly selected adults showed that 21% of respondents smoke. So what we want to do is express the original claim in symbolic form and identify the null and alternative hypotheses. So it says claim 20% of adults smoke. If they're giving you a percentage, then that means we're talking about a proportion. So our claim is about P. So the claim says 20% of adults smoke. So that means we're claiming that P equals 0.2. Once I have my claim, then I need to set up my null and alternative hypotheses. So we're always going to use the same parameter. So in this case, both my null and my alternative hypotheses should be about P. Remember that the null hypothesis should always have an equals. So in this case, our claim and our null hypothesis are going to be the same. Our alternative hypothesis has to be the opposite of this guy, in that if we're saying that our claim is that P is 0.2, the other possibility that exists is that P is not 0.2. And that is all our alternative hypothesis in this case. Part B wants us to make a subjective estimate to decide whether the results are significant, and then state a conclusion about the original claim. Now, when it says subjective estimate, that means we're not going to be using the critical value or the p-value estimate. It's just going to be based on the information that they gave us. So in this case, this was our claim. And then the additional information is that they surveyed this many people and that the results showed that 21% of respondents smoke. So subjectively, we are trying to decide, well, is 21% close enough to 20% that we might think that this claim could be true? And the reason why it's subjective, maybe you have a different opinion than I do, but I would say that 1% is not a lot to be off by. So I would say that since 20% is approximately 21%, that means that we would fail to reject our null hypothesis, meaning we're saying that it is possible that 20% of adults smoke based on this information that we've been given. Now, it says state a conclusion about the original claim. That's what this table is for. So I need to look now and I need to decide, does my original claim include equality or not? Original claim is right here. It has an equal sign, so yes, it includes equality, which means I'm looking at either this guy or this guy. So now the second thing I have to look at is whether we rejected or failed to reject. And in this case, it says failed to reject. So includes equality and failed to reject is the bottom row. So we're going to word it exactly like it's worded here. So we say there isn't sufficient evidence to warrant rejection of the claim that, and then we say what the original claim was, in this case, 20% of adults smoke. Okay, so if it says subjective, that means you're just looking at the claim versus the data that they gave you. You're not actually, doing any type of testing yourself. In example 2, it says use a 0.01 significance level to test the claim that when using X sort, the majority of babies born are girls. In a sample of 100 couples who used X sort, 55 had baby girls. Okay, so first thing we need to do, and again, if you look at the front of your notes, now we're actually being asked to test the claim. So this is all the steps of hypothesis testing. So the first thing we need to do is identify the claim and express it in symbolic form. So the claim is that when using X sort, the majority of babies born are girls. So we have to think about what it means when we say majority. So majority means more than half, which that is like a percentage, which means that this one also is a proportion. So our claim in this case is that P is greater than 0.5, meaning more than half of the babies born are girls is the claim. Once we do that, again, I'm just looking right here and going right down the line. Next, we already did the symbolic form. Now we're identifying the null and alternative hypotheses. So the null hypothesis always has to use an equals. So when we look at this case, we're talking about P and our value is 0.5. So our null hypothesis is going to be that P is equal to 0.5. Our alternative hypothesis, different from what we did in example 1 because of our claim. Our claim is that it's not equal, that it's bigger. Whatever your claim is, that is either going to be the null or it's going to be the alternative hypothesis. It has to be one or the other. So since it can't be our null because it doesn't have an equals, it means it has to be our alternative hypothesis. So in this case, the claim is our H sub 1, which is P is greater than 0.5. The other thing that we're going to need to do is we're going to need to write down various values that we know because we have to find our test statistic. So when you look at our test statistic chart here, we're talking about a proportion, which means we're going to use the Z for our test statistic, and this is the formula. So I need to know P hat and P and P and Q and N. So they gave us some values. They said in a sample of 100 couples who used X sort, 55 had baby girls. So this is a sample, so that value is our N. So N equals 100. since it says that 55 of them had baby girls, that's giving us our p hat. So p hat is 0.55. So now when I go to find my test statistic, I'm going to use, so my test stat, I'm going to use z equals, and then this formula again that's right up here. So p hat minus p divided by the square root of pq over n. So p hat is 0.55 times p, which was 0.5, divided by the square root of p times q. So if p is 0.5, then that means q is also 0.5. So this is 0.5 times 0.5, which is 0.5 squared. And then n, which is 100. So when I do this, I get 0.05 on the top. On the bottom, I actually also get 0.05, which means that my test statistic is 1. That's my z. So this is my test statistic. Then I'm going to show you how to use both methods for testing this claim. So if I am using the critical value method, then that means the first thing I need to look at is what type of tail I need to use. So down here, I look at my alternative hypothesis, and it was p is greater than 0.5, which means this is a right-tailed test. And so what I am trying to find is the area that has my significance level to the right. So in this case, it tells us that we're supposed to use a 0.01 significance level. So if I draw that in picture form and it's a right tail, that means I want an area of 0.01 on the right, which most of our calculators only do areas to the left. So that means the area to the left would be 0.99. And so in this case, because we're using a z distribution, the normal distribution, that means that to find the critical value, we are going to use our inverse norm. So I do inverse norm of 0.99. And I am using the normal distribution, the standard normal. So you are just keeping this at 0 and 1 for your mean and standard deviation. So area of 0.99, 0 and 1 as our mean and standard deviation gives us a critical value of z equals 2.33. Sorry, that doesn't look like an equals, but that's supposed to be. So that's our critical value. P-value, if I go to find that, p-values, I am finding the probability, and if you go back up to where we had our p-value, the probability of getting a value of the test statistic that is greater than or equal to the sample test statistic. So we already found our sample test statistic. We are finding the probability of getting something that is greater than or equal to that. So we use normal CDF. So in order to find, I'm doing, in this case, the probability of Z being greater than or equal to 1, which because that's our sample test statistic is 1. And so if I do that in my calculator, that means I'm going to normal CDF, and the lower limit is going to be 1. The upper limit is going to be all the 9s. So I'm trying to write small here to fit it in so we still have room. So normal CDF, and then that's of 1, 9, 9, 9, 9, 9, or you can write an infinity symbol if you prefer, with a mean and standard deviation of 1. And our p-value, p-values we round to 3 significant digits because they're from a probability. So 0.159 is our value there. Now, in most cases, we're not going to do both of these. In most cases, it's going to tell us use the critical value method or use the p-value method, or you get to choose. We normally wouldn't do both. I'm doing both because I want to clearly illustrate for you what you need to do in both cases. So, based on the critical value method, we make our decision based on whether or not our critical value is in the rejection region or not. So in this case, our rejection region, because it's right-tailed, our rejection region is over here, right? And the value that we found for the critical value, that this cutoff right here is 2.33. So meaning we're only going to be in the rejection region if our value is bigger than 2.33. So in this case, 1 is not bigger than 2.33. It's not in the rejection region, so that means that we fail to reject our null hypothesis. If I use the p-value method, when I look at it, remember that p-value decision is based upon whether or not, and you can see this in the original things, we make our decision to reject if the p-value is less than or equal to alpha. We fail to reject if the p-value is greater than alpha. So our alpha in this case was 0.01, that's our significance level. So our p-value, which is 0.159, is bigger than our 0.01. So that means that we fail to reject. So now, since we have failed to reject, we have to word our final conclusion, and that's what we do here. So our original claim was that P was greater than 0.5. So that means the original claim does not include equality. So that's these first 2 rows. We failed to reject, so that means this row. So we write, there is not sufficient evidence to support the claim that, and then we write out the original claim. So there is not sufficient evidence to support the claim that when using XSort, sorry it's so squished here, running out of room, the majority of babies born are girls. I know, like, your hand's gonna be cramping up and you're gonna be really annoyed that you always have to write this out. But yes, the answer is you do always need to write it out. If you want to, like, abbreviate some of the words, like sometimes I'll just put SUFF for sufficient or EVID for evidence. But you do need to write out the claim and you do need to use that exact wording. Okay. Last one, example 3. Researchers are interested in the mean age that adults make a big career change. In a random sample of 40 people in the population of interest, the mean was 27. Use a 0.05 significance level to test the claim that the mean age is different than 30. So I've tried to pick examples where the wording is not directly clear. Sometimes it will be directly clear, but in example 2, it just says the majority, so we had to kind of interpret that that means greater than 0.5. Here, when it says test the claim that the mean age is different than 30, that means that our claim is saying that it's not equal to 30. So in this case, our claim is that mean, so mu for the population, is not equal to 30. Remember that our null hypothesis always has to have an equal sign. This is not an equal sign. That's a not equal sign. So our null hypothesis then has to be that mu is 30. And remember that the claim itself always has to be either the null or the alternative. So in this case, it has to be the alternative. So our alternative hypothesis is that mu is not equal to 30. So now I'm going to go through, and again, you don't have to do both every single time, but I would, on ones that don't specify which method to use, I would rotate. Use the critical value method for some of them, use the p-value method for some of them. Here I'm going to show you both again. So our test statistic in this case, so we look back at our chart here, which statistic do we know? So in this case, we don't know the standard deviation, and our n, let's see, sample of 40 people, so our n is greater than 30. And so we're going to use our t here. So we have x bar minus mu over sample standard deviation divided by the square root of n. I just noticed that on this one it says sigma not known, and that's actually a typo. Otherwise, how would you tell the difference between these? This one will use normal if we do know the standard deviation, this one when we do not. So we're using the student t because we don't know the population standard deviation. We can look and find the sample standard deviation, but we don't know this particular value. So now I'm going to go back here. And our test statistic we just decided was t. So t equals, and our values say to do x bar minus mu. So x bar is the sample mean, which is 27, minus mu, which is the population mean. So what we're testing is it being 30. So minus 30 divided by, and then we need the, oh, I made a typo here too. I forgot to give you the standard deviation when I typed this out. That would be helpful. Sorry, I just went to plug it in and I'm like, where is the sample standard deviation? Sorry, the sample standard deviation given is 4.5. I just forgot to type that out in the guided notes here. So sample standard deviation is 4.5 and then divided by the square root of n. So sample was 40 people, so the square root of 40 would go here. And so when I do all of this in my calculator, I should get negative 4.22. So this is our test statistic, is negative 4.22. So now, because I'm going to do all of the methods again, our critical value in this case, because our alternative, and again, for the first few, I'm showing you where to look. Eventually, you'll just know and not have to look at these things. But the sign used in our alternative hypothesis was a not equal. So this is a two-tailed test. So that means when I draw the picture, I have part of the rejection region on each side. So if my alpha is 0.05, that means that that 0.05 is split between these two ends. So that means this side is 0.025, and so is this one, 0.025. So in this case, we are looking, our test statistic was negative. So when we're looking at the critical values on a two-tailed test, there are two of them. But I know that because this is negative, that I'm only going to care about the one on the left side. Because in order for it to be in the rejection region, it's going to have to be below whatever this guy is. So I don't really care about the right one. Now make sure you use the right one. Our test statistic is t, so I need to do inverse t, not inverse norm. So go to our inverse t, so second distribution, choice 4. The area that we're looking at is on the left side is 0.025 because I'm trying to find this guy right here. So I want this area. So area 0.025, degrees of freedom, remember, is n minus 1, so in this case 39. And so inverse t of 0.025 with 39 as our degrees of freedom. So our critical value is negative 2.02. So that's this guy. The positive version, just so you know, would be positive 2.02 because in this case, remember, we're using a standard, so we have positives and negatives symmetrical on each side. All right, now I'm going to find my p-value. So p-value in this case, because it is two-tailed, we have to be careful because what we are doing when we have our p-value is just, we have to look at both sides. So whenever you have a two-tailed test, you have to make sure that we multiply whatever our probability is by 2 because it's a two-tailed test. So in this case, remember that when we're using the p-value method down here, what we're doing is we're finding the probability, so by definition of p-value, the probability of getting a value of the test statistic that's greater than or equal to the sample test statistic. So in this case, because we have the left side that we're looking at, we're looking in this case of the probability of t being less than the value. So probability of t less than negative 4.22, which is our test statistic over here. So when we do this, so that means we have to do 2 times whatever we get from doing normal CDF of lower limit negative infinity, upper limit negative 4.22, with 0 and 1 as our values. Now, when I do this in my calculator, I get scientific notation. Please, guys, you have to look at the whole thing, because I'll get a lot of people on ones like this that'll just put 1.222. That's not what it says. It says 1.22 blah, 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 e to the negative fifth. That means that I have to move that decimal place 5 places to the left. So when I do that, the decimal place was here. So if I move it 5 places over, that means I'm going to have 4 zeros. 1, 2, 3, 4. When I multiply that value by 2, then that's going to give me 4 zeros. 1, 2, 3, 4, 2, 4, 4. Okay, so just make sure we're paying attention to that. So this is my p-value. So I've got my p-value, I've got my critical values, and I've got my test statistic. So now when I look using the critical value method, remember that I'm looking at whether the test statistic would fall in the rejection region. So meaning, is my test statistic in this shaded region down here? Well, the boundary is negative 2.02. Negative 4.22 is less than that. So we would say negative 4.22 is less than this guy. So that means it's in the rejection region. So we're going to reject the null hypothesis. For the p-value method, remember that what we're looking at is whether the p-value that we got is less than or greater than our significance level. So in this case, our significance level was 0.05. So my p-value, which is this guy, is less than 0.05, which means, again, eventually you'll just know this, but for now, if you look here, p-value less than or equal to alpha means reject. So that means we are going to conclude to reject. Most of the time, you are going to get the same answer using the critical value method that you would get using the p-value method, which is why I've said a couple times, and I'll say it one more time here, if it doesn't tell you to do a specific method, choose one or the other and rotate which one you choose. You do not have to do both the critical value and the p-value every time. So now we just need to word our conclusion. So in this case, we look at our null hypothesis, which was a not equal to, and our reject. So I go back up here. Original claim does not include equality, so that's these two. We rejected, which means we say there is sufficient evidence to support the claim that, and then we fill in our claim. So there is sufficient evidence to support the claim that the mean age of big career change is different than 30. Okay, I know that took a really long time. That's why we are having 2 days for this lesson, so that we can get all the information and then we can spend time on the practice problems. So Make sure you've got everything written down. Go back to things if you need to rewind the video, but hopefully that gives you a good idea of how to start some of those problems.